a tool that we call Restrictifier. The main motivation for this tool is the fact that static compilers usually do not have enough information to eliminate pointer aliasing in source code. And from this fact, the compiler usually cannot apply aggressive optimizations to a program in the presence of aliasing. So what this tool does is to apply a set of static analysis to a program to try to eliminate as much aliasing as possible. We provide a website for our tool where you can check things, for instance, like how to compile and install it. If you want to download the source code for it and compile and install on your machine. Or you can also use the website itself to upload and try a simple example. Uh, you can even upload your own code. In this demonstration, we will be using the example provided on the website itself. So this example is a simple prefix sum of arrays. Okay, so the prefix function takes two arrays as input. And the thing is that the compiler doesn't know if these two pointers can point to each other, if these two arrays can point to each other. And when the compiler doesn't know that, it can't apply aggressive optimizations like code vectorization and redundancy elimination. Okay, so what our tool does is to iterate for all call sites in the program, in this case this call to prefix here, and try to statically apply alias analysis and see if the pointers can be shown to do not point to each other, like in this case. And if so, it simply replaces this version of the prefix function by a version where the arguments are marked as not being alias, so the compiler can take advantage of it. So we simply hit compile the source code to get an output. At the bottom of the screen, you can see simple statistics about the compilation, like the number of call sites replaced. In this case, we can see that we replaced one call site, which is exactly the call to the prefix function here. We also provide, in case you want to execute in our machine and see the time difference on the optimized and in the original versions, we provide their LLVM assembles. To use you have simple instructions here how to use them, how to compile and produce actual binaries for them, okay? And you have to use LLVM 3.6. We already have installed LLVM 3.6 on this machine, and we will be testing these assemblers here. So you can simply download both of them, the original version of the optimized version. We're gonna download both of them again, just to show how to compile it. Okay, so we downloaded both assembly files, and we have previously generated the CFGs for these assembly files. On the left side, you can see the CFG for the original version. So we have highlighted some important parts here. So in the original version, you can see that there is a store in the innermost loop. So there is a quadratic number of stores in the original program on the size of the arrays. In the optimized program, however, you can see that there are stores only in outer loops. So the compiler was able to extract the store to a temporary variable, thus reducing the complexity of the number of stores to a linear complexity. You can also see that the compiler was able to vectorize the program. Here you can see that we have a simple addition in the body of the inner loop. Here we actually have, in the optimized version, we actually have vectorial additions where you can add up to 4 numbers at the same time. This part of the code corresponds to this part of the prefix function, where you have the actual sum. So the optimization that we saw in the screen is the fact that this load was removed to before this code, and the code itself was vectorized, the innermost loop. Okay, so now let's try to compile and execute it to see the time difference. First, we are going to compile the original version to see how it goes. So we just compiled it. We just use our LVM 3.6 to compile the assembly file, and we are going to run it to see the execution time. Okay, so it took it took more than 11 seconds. Now we are gonna compile the optimized version and see the difference. Now we execute it, and we can see that's much faster, like 10 times faster than the original version. And that time difference is due to all the optimizations that I just explained, like vectorization and redundancy elimination. Okay, uh, so that's it for today. The source code for the tool is available for download, and in the website, as I said, you can find instructions on how to compile and how to install it. Thanks for watching.